All right, we're back with more coding. So let's continue. Let's continue our efforts with data generation, right? Because we used Siona already. We kind of used it halfway, and we managed to generate MIMO wireless channels for many transmitters and many receivers. But they're still in the time delay domain. Okay, so if we, let's see, what do we have here? I think we had this plot, okay, which shows us how a channel evolves in the time axis. A 2D channel evolves across the time and delay axis for a very fast moving receiver. So the time axis is fine. These are different snapshots at different physical times. The only thing we need to get rid of is this delay axis, because it sort of has the information spread around. You can think of the delay axis as a micro time scale, right? Time is a very coarse, the x-axis here, the time axis is a very coarse time scale. The delay is a very fine scale. We're talking about nanoseconds between the vertical plots here. And that there is a trick they do in wireless systems is if a user only captures a frequency band, which you may have heard, I mean, you probably know this from your phone, right? Like it works in certain frequency bands. Then that's the equivalent of a user experiencing a singular frequency in the Fourier transform along the delay axis, okay? So what are we gonna do today is we're gonna have to finish the data pipeline, and we're gonna move from the delay to frequency axis, where we finally get the channel, a 2D channel matrix at a given time and frequency. Again, the time axis doesn't bother us, right? Imagine we're just picking a time point. It's either now or 5 seconds later or whatever. This is physical time. But the delay axis, these channels are sort of, it's like the micro time scale. And that's not how wireless systems work. Like you're not actually gonna wait for the delays to finish. Instead, you're gonna take an instantaneous snapshot of a single frequency. And to do that, we have to convert this whole axis to frequency domain and just take a snapshot of it, which is called a subcarrier or a subcarrier frequency, okay? So for that, the basic tool, we're not gonna do it, but Siona does it. Maybe it's worth recapping, is the Fourier transform, right? So the Fourier transform is pretty easy because well, if you have some signal processing background, but even if you don't, it's not that hard to understand. What it does is it just takes a signal in the delay domain, okay? And let's put it this way, it's a very sparse signal, okay? Because we see this in our plot too, okay? There's only 13 delay taps here, and they all have certain values and amplitudes, right? And when I say this, imagine we only look at one entry of this matrix, like just the 1-1 entry, right? So then that signal in the delay domain would just be a bunch of sticks, right? So first of all, it would be a value, let's draw them with red, right? So it would be a value at time 0, at delay, sorry, I messed up, I should not have said the time, right? Because time is different, this is the delay. And then usually, even at the micro scale, this signal kind of fades out, as you can imagine, right? We can also see that in the plot, right? Okay. So this is kind of how it would look like, right? Well, so it basically takes this and it converts it to a frequency domain, which is gonna be continuous now. So this is actually gonna look, I can't even draw this by hand. But again, it also has a gain now. But it is going to look wildly different, because if it will no longer be sparse, so this will be the frequency domain. continuous signal. Okay. And do I have a free draw here? I do have a free draw here. So it's gonna look, I'm just making it up, something like this way, that this will also be sampled, but on a uniform grid now. And this is finally the channel per user, right? So this will be something like this. Again, very important is that it's uniform grid. So then this is really how your phone works, pretty much, okay? So what happens is, in real life, users are... Now, because this, remember, this all happens, this plot here were... Let me space these equally nicely. Okay, very good. So, again, let's recap. So we started with data in a giant grid, and we picked the time point. Okay, then we converted from delay to frequency, and this is called OFDM, which is multiplexing users in the frequency domain. What happens is, these are now 1, 2, 3, 4, I don't know, 5. These are 9 different users. These are 9 cell phones. They're actually 9 cell phones. Like, this is literally how 5G and even 4G worked, and probably nothing's gonna change in 6G. So now the users, they all communicate together. Like, this is you and 8 other phones receiving data from the base station at exactly the same time, because remember, we picked the time point, but at different sub-frequencies, if you want, right? So this is why the Fourier transform allows us to go from the delay domain, where users would have to take turns in time. Okay, so another way to view it is, let's say this technique of jamming multiple users together is called multiplexing, right? And this is pretty much this is why phones or cellular communications work as well as they do, because if you're in a building with 20 neighbors, you can all use your cell phones, say, at the same time. But what happens behind the scenes is there has to be a way to multiplex you. So there's 2 ways to do it. You either take turns in the delay domain, like a round robin thing, right? Like, you get a batch of data, like let's say all 20 people are downloading images. Each one of them is downloading a different image, right? They would be either multiplexed in the delay time grid, or they would be multiplexed in the frequency time grid. The advantage of the frequency time grid approach is that it actually allows 2 people to use their phones exactly at the same time. They just have to filter a specific frequency, instead of having to actually keep track of delays and all that stuff, which was really never a thing. It was always frequency multiplexing. I may have garbled that explanation a bit, but it's pretty much how modern communication systems work. Okay, so then finally, in any case, we can finally go back to coding now, because let's see. So we have the path gains and the delays from Siona. We spent a lot of time plotting them. Oh, there we go. Oh my God, Siona had this. Okay, I didn't even know it had this, but yeah, it had a plot too, which is exactly what we talked about. And there's also the time evolution of a path gain. This is the large scale time. Finally, we want to look in the frequency, and here it is. This is exactly the Fourier transform that I showed. So we're gonna want to convert this to frequency, and this is just like literally 2 lines then, right? There we go. So we just get so we get the frequencies, because remember we said they are uniformly spaced, but they have. So let's remove this then, because it's kind of a dirty plot. Okay. So we get the frequencies, and then we finally get this H frequency. And this is called gains for us. And this is it now. This is the MIMO channel matrix we're gonna train a diffusion model on. We're actually done. Wild, right? Yeah, we don't care about this. We'll use the simulation later. Okay, so we can print shape of the channel of the frequency domain channel. Let's see how this looks like. And it will be href.shape. And let me do it this way. So let's, okay, so now we can finally go back. We can clean this code up because it's really bothering me. So now if I run a giant UV run pre-commit run all, it's gonna significantly clean the code up. Okay, there we go. All the spacing is nice. All the dead imports are gone. We don't really need the delays anymore. We can start cutting these a bit, right? We actually never needed this, so I don't know why the heck they want us to do that. We don't even need the stream management. We just need the resource grid. We don't need this. Again, there's a lot of parameters here, like the subcarrier. Oh, here's an interesting one, the subcarrier spacing, right? This is exactly the spacing that I was trying to draw here between two of these frequencies. Now, of course, Siona takes care of everything for us. We don't really have to simulate this. Carrier frequency, blah, 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 blah. Let's not even do the plot. Let's just see the shapes. Well, no, wait, I want to see the plot in frequency now. So what we're gonna do is, I don't want the delay, I don't need the delays anymore. Instead, we're going to plot H frequency now. So we're gonna call this frequency, I guess. Oh no, but we hard-coded this function. Oh, this is so dumb because we hard-coded the function for... All right, so... Good. Let me do something else. Let's see fatter channels. Well, no, let's see a 4x8 channel, but... So what do? UV run with group Siona, MIMO.c-m, MIMO.cdl. Okay, we're done. So shape of the frequency channel. So 32 samples. These are fake axes here. We can squeeze these out. We should actually now permanently squeeze these out because we're done now for good. We're actually done with Siona, so we just wanted to get to this thing. So let me do this and print again, okay? So 32 samples, 32 independent data points, 4x8 size for each matrix, 14 time. Each channel is taken at 14 times, so we have a time evolution of the channel, and 76 subcarrier frequencies, right? So now what we're gonna do is we're not gonna plot 76 plots. That's way too much for 2D, right? But let's plot how let's space these out a bit, right? So H frequency 0 cuts this, everything, all the times. And let's say we want to plot from, what is 76 divided by how much is, if I divide by 4, 19 points, by, I guess by 8, right? So we're gonna have 9 subcarriers. So we're gonna have a 9 plots on the frequency dimension. Okay, it does look okay. Perfect, very good. So this is a real MIMO channel. Okay, so now we're really ready to do a generative model here. So there is structure here, right? There's time variation, there's frequency variation. So finally, what we're gonna do is we're just gonna take snapshots from this grid and we're gonna train a generative model to generate regardless of time. Just we're gonna jumble all these matrices together. Now remember, these are complex values though. We're only seeing the absolute value. There's a phase plot too, which I'm not gonna show, but this is finally what we're gonna train the generative model on, right? So this is a pretty complex MIMO channel now because the users are, there's a lot of scattering, right? There's no more groups of antennas that are sort of clumped together. It's 4 receive antennas, 8 transmit antennas, and the gains look different. So then what we're gonna do is we're just gonna sample this grid, and that's it. Now we have the batch dimension, we have everything, so we can actually generate the training and validation data set of tens of thousands of channels. So let's do that systematically now in Python, okay? To do AL. Okay, we don't need the IM here. Let's clean up the code. Sort of tempted to not even include this. Nah, I'll include the plot function for now. Okay, so we can actually commit this to GitHub. It's pretty clean. CDL, okay. What did we change in data? src MIMO data, anything? Oh, I see, a placeholder. Okay, yes, we will have to unify that at some point. Yes, I agree. So git commit. Full pipeline for getting frequency domain channels. So we have this. Finally, we have 2D matrices, complex valued. You can, if you watch the previous episodes of the series on YouTube, we already have the deep neural network that's supposed to be trained on 2D complex data. We're doing a bunch of complex to real stuff, blah, blah, blah. Let's generate the tensor data set. I'm gonna cut some of the prints though. Now well, you know what? Let's do it this way. What's nice is usually you do a verbose Boolean, okay? If some users really want to plot all this, they can just do if verbose, okay? And they can do all these prints and plots after. Okay, and this will be if config.verbose. Okay, so we're gonna run with it false. We're not gonna plot anymore, but this will create the, it'll print the shapes and create, so move to frequency domain. And that's it. So now let's generate a large scale data set, right? So what we're gonna do is, we're just gonna increase the batch size, right? So num, very important, is will be num samples. How many channel samples do we want to generate? Integer, and let's say it's 10,000 by default, okay? So then we're just gonna pass the batch size here. We config num samples. Okay, that's done. Now, remember, we're gonna end up with a giant 2D tensor. So subsample data at random in the time frequency grid, okay? So what we want to do is we want to say data, and finally we're gonna data set, let's call it like this, okay? Actually, I think now is a good time to, yeah, we should convert this to NumPy. We're done. We can move to NumPy world forever, okay? So then now this just becomes NumPy.absolute value. So we're done with TensorFlow world. So now we have a big tensor, which I believe, if I remember correctly, was 5D, right? It was, what was it? Batch. Well, we had this in the document somewhere. Okay, I don't know where it was, but it was, I think it was batch, RX, TX, time, and frequency. So what we're gonna do is we need to get batch rx/tx. Okay, we need to collapse these. Instead of, now a really cheap way to do that is to just say ... 0 0. So we're going to take the first time and the first frequency, and that's it, this data set. But we don't want to do that. We want to subsample a random time and frequency, so we get a bit more variation. And maybe in the future we can add some constraints. We only want to sample middle frequencies or something. Okay, so how the heck do we sample a tensor at random? Or not a tensor, but a NumPy high dimensional array at random. Let me think here. So what do we do here? I believe this is a good NumPy experiment, right? So let's say we have A. So we're gonna need NumPy because we're in pure NumPy world. So we have A as NumPy random of size 8, 4, 4. What? Oh, it wants the shape. Okay, I forgot. I haven't used NumPy. No. Oh no, sorry. It's random dot rand. Oh, come on. Okay, so we have an A. Okay, so we have an A, which is a matrix of, now we would like to sample a random position. I believe it's something like this. So random rows or random times would be NumPy random randint from 0 to the shape of that axis. Okay, and the size of this will be the number of data points. So now this is the index that we want to pick in the first axis, and then the other one is exactly this, but the second axis, and it's still one for each data point. Okay. Now I think if I magically do... Nah, there's no way this will work, right? It does work. Oh, but it doesn't do what... No. I know what it is. It's first you sample... Okay, I know, I remember now. So first you sample the row and you take everything. Then... So now you have... What is this? No, because it picks too much. Oh, come on. So A shape is 844. So I want to pick a random index here and another here, repeated 8 times. So I only end up with 8 numbers. I know what the indices are because I have random times and random frequencies for those axes. I think it's like this. You can do a triple indexing trick, because if I take from here range length or A shape 0. Yes, okay. So the way NumPy works is if you index all the axes with indices of the same shape, you can jointly index in the tensor. Now if I look at the first element I picked is 0, 7, 7. But this should also be A0 random times 0 random frequencies 0. It is. The second element in B should be the second data point at the second random time at the second random frequency. It is, okay? And so on and so forth. So this is, in NumPy, you can index all the axes at the same time. And notice this is a fake axis here because it just goes 0, 1, 2, 3, 4. So it's paired with these guys, okay? So then this will be range, shape 0. Oh shit, but I have two. Oh, the problem is even more complicated. Oh my god. Okay, so we solved it like this. Okay, it's even worse in our case because A is now... Okay, this is... I haven't done this in a while. It's pretty interesting. So now the problem in our case is we have an 8, 3, 3, 4, 4. Again, it wants tuple, or what's happening here? Yes, okay. What? Wait, I can't do normals in... This is wild. So I can't do NumPy random normal. It only works up to 3D. I'm so dumb. What function did I use before? How did we get the A? Oh, it's random rand. Okay. Okay, NumPy is a bit inconsistent with how they use these things. Okay. The problem is now, if I just do B equals, so let's try to do the trick here. I don't think it'll work though. Range A shape of 0. I want everything here and everything here because I want to keep the 3x3 matrices. I want to get 8 3x3 matrices, right? I want to sample these two axes, so I can try to put random times random frequencies. It does work. Okay, perfect. So now if I look, what is the first matrix that I picked? Okay. Consequently, who should this be? The first index, everything, because I want the full matrix. The first random time, the first random frequency. It is. If I look at B, the fifth or whatever, it should be A5, the fifth random time. Okay, perfect. So we're done. So it's really easy then. I want this, keep, and I have to the trick is to pre-sample the times, right? So random times, random frequencies. I guess I'm gonna use, there's an even cleaner way to write this because if I use dots, it starts to take the dimensions from the end. So then I can address the random times as NumPy random randint from 0 to h frequency dot shape -2, the second from the tail, size h frequency dot shape 0. Well, actually, there is a nice name for this. It's called config dot numsample. So let's try to use nicer names here so we know what they mean, right? So okay, so then for each sample here, config num samples, and this one is the twin but on the last axis. Okay, so now this also informs me how these are arranged because random times random frequencies, they come in order second to last. And this also allows me to have as many axes here. Now I can do even wild stuff now, like you know, we can keep like 3D matrices now, and we just do B is equal to, and all I do is we do ... and there we go. So now we kept 8 3 3 3 by cutting into the last two axes. Well, shit, that's it, right? Return data set. No, we can't because, okay. So one more thing to do is we're gonna have to save this to disk because of the Siona limitations, we actually can't run this at the same time with PyTorch. We covered this earlier. We had to do UV dependency groups because unfortunately the library is kind of bad. So it's actually incompatible with diffusers and modern NumPy. So what we're gonna have to do, the final thing is we're gonna have to save this to disk. Oh, obviously we want to index this. Sorry, it's not a function, my bad. So there's a basic syntax mistake here. It's indexed at these, it's an array indexing. This should do it though. Interesting, so we can, I mean, I think I've seen this before. Okay, finally we have data. This is an H5 file. Then we can just try to load it directly here, right? So import H5Py. File name will be data slash, I'm just gonna take all this and copy it. Okay, .h5. How the heck do I load an H5 file? How to load H5 file in Python. With read as f, keys. Okay. So it's just f of data, I'm guessing, right? Well, let's see. So h5py dot file name r. I'm gonna keep it permanently open, right? Okay, and then what do I have here? F dot keys. Obviously, it only has data, and I can do data f dot data, and that's it. Yes. Okay, this is the data. Okay, that's it. So I'm guessing it's also real data, right? Like, yeah. Okay. Do I have to do like 2 NumPy or something? Is it NumPy as array? NumPy as array data. Yes, it is. Okay, so finally we got the NumPy array back. Okay, so we're good. We have the whole pipeline. We had the whole data generation pipeline, so we're gonna have to chunk the data generation manually, which is a bit annoying. We can do that next time. We can try to figure out what the max data is. Because we're also gonna want to increase these drastically for more richer channel simulations. But yeah, this was it for this episode. So a lot of progress, and we'll keep working on a data pipeline next. Thanks for watching.